Hi there, and welcome to this lesson on pure mathematics. In this lesson, we're looking at complex numbers, and in particular, we're looking at the exponential form of a complex number and Euler's identity. First of all, apologies if the background noise does get a little bit loud at times. It's the sound of rain falling on a tin roof. Now, numbers, they can be split up and categorized in various ways, but the two big categories are, first of all, the real numbers, which includes the positive integers, the negative integers, the number 0, rational numbers, which are numbers that it is possible to write as a fraction, and last of all, irrational numbers, which are numbers that it is not possible to write as a fraction. Numbers like √2 and the cube root of 5, pi and e. It is impossible to write any of those numbers as a fraction. And one of the consequences of that is it is also not possible to write any of those numbers as a decimal. In each case, they would be infinitely long decimals that have no pattern whatsoever. The choice of the word irrational does feel like a good choice. It has the same etymology as the English word irrational, and in the original Greek, that word can mean unreasonable, but it can also mean unsayable. And in a very profound sense, irrational numbers are unsayable numbers. They cannot be said as a fraction. They cannot be said as a decimal. You can never quite get your head around exactly what number they are. The second big category of numbers is complex numbers. Complex numbers are numbers which can be written in the form x plus yi, where x and y, they're just normal numbers, they're real numbers, and I is the strange part. I is equal to the square root of -1 and is called an imaginary number. And again, the words complex and imaginary feel well chosen. There are several different ways of representing complex numbers. The way we were just looking at is called the Cartesian form, where you have z equals x plus yi. So you have something like z equals 5 plus 3i. Graphically, it's possible to represent complex numbers on what's called an Argand diagram. On an Argand diagram, the x-axis shows the real part of the complex number, the value of x. The y-axis shows the imaginary part of the complex number, the value of y. So if we had 5 plus 3i, you just plot that like a normal coordinate, 5, 3. And sometimes complex numbers are just represented as a point, as a coordinate. Sometimes they're represented as a line or a vector, in which case you'll have the length of that line r and the angle that the line makes with the x-axis going anti-clockwise. R, the length, is called the modulus of the complex number, and theta, the angle, is called the argument of the complex number. And there is a relationship between r, theta, x, and y, and you can get it just by using basic trigonometry. X will be equal to r cos theta, and y will be equal to r sine theta, just using the right angle triangle we have there. And substituting those values into the Cartesian form gives us what is called the modulus argument form of a complex number. That is frequently written with the r taken outside the brackets and cos theta plus I sine theta inside the brackets. And sometimes it's abbreviated even more to what is called the polar form of a complex number, where you just write the argument and the modulus inside the brackets, r theta. So several different ways of representing complex numbers: the Cartesian form, the graphical form, the modulus argument form, where if you need to calculate r or theta, r you'd find using Pythagoras, the square root of x squared plus y squared. Theta you'd find using trigonometry, the inverse tangent of y divided by x. The polar form, where you just write down the modulus r and the argument theta. And now we meet what is called the exponential form of a complex number. Now, in order to derive that, we need to look at the series expansions for sine theta, cos theta, and e to the x. So cos theta can be written as 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, and so on. Sine theta can be written as theta minus theta cubed plus theta to the 5 over 5 factorial, and so on. E to the x can be written as 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now, in that last expansion, if we let x equal I theta and substitute that in for x, we'll get the following. 1 plus I theta squared plus I theta cubed over the relevant factorials. And substituting on the left-hand side, we get e to the I theta equals this expansion. Multiplying out the brackets, every time we get I squared is minus 1. So every time we get I squared, we'll get a minus appear. So multiplying out the brackets will give us that 1 plus I theta, and then the I squared becomes minus 1 in the squared term. In the cubed term, you get I squared times I. So you get a minus, but you still have an I. The following term, we get another I squared, times it by minus 1 again gives us plus, and so on and so on. If we then separate those into the two halves, you'll notice some of them involve i's, some of them don't involve i's. So the real part, we put in the first bracket, 1 minus theta squared over 2 factorial, and those terms. And then we've got the imaginary part on the right-hand side, with I taken outside the brackets, and that'll leave us with theta minus theta cubed over 3 factorial, and so on. Now, the three significant expansions there are for cos theta, sine theta, and e to the I theta. And if you look carefully, you'll notice that the real part of the expansion for e to the I theta is identical to the expansion for cos theta. And the imaginary part of the expansion for the e to the I theta is identical to the expansion for sine theta. What that means is that cos theta plus sine theta, if we combine those series together, it will give us the bottom series. It'll give us e to the I theta. Now, several different ways of representing complex numbers. The Cartesian form, the graphical form, the polar form, the modulus argument form, and we now have the exponential form. Z equals, and if you look at the modulus argument form, you've got r into cos theta plus I sine theta, and we just substitute in what we did just now. That is identical to e to the I theta. So the exponential form is z equals r times by e to the I theta. All of these are saying exactly the same thing. They're just saying it in different ways. And depending on what question you are doing with complex numbers, one form will be more helpful or useful than the other. Now, the formula that we derived just now, cos theta plus I sine theta equals e to the I theta. It's a very important relation, and it has a name. It's called Euler's relation, named after the Swiss mathematician Euler. If we let theta equal pi in this formula, something quite remarkable results. Putting in theta equals pi, we'll get cos pi plus I sine pi is equal to e to the I pi. Well, cos pi is minus 1, sine of pi radians is 0. So we get minus 1 plus 0 equals e to the I pi. This result, which is called Euler's identity, can be written in two ways, both of which express something extremely surprising. First of all, we could rearrange it to give e to the I pi plus 1 is equal to 0. And in this identity, we have the 5 fundamental constants of mathematics. We have 0, we have 1, we have pi, we have e, and we have I. And they're combined together in the most elegant fashion. And I think even more surprising than that, if we choose to rearrange it so that we have e to the I pi equals minus 1. These three numbers on the left-hand side, e is an irrational number, pi is an irrational numbers, numbers that are unsayable, impossible to write as a fraction. There is no decimal which is the same as them because they're infinitely long and have no pattern to them. They're the most troubling numbers you meet, except for I, which is more troubling still. It's a complex number. It's the square root of minus 1. And these three famously unknowable and intractable numbers are then combined together in a highly complex power, e to the power of the square root of minus 1 times by pi. And for the result, you get simplicity itself, minus 1. That is the end of this lesson. Thank you very much for listening, and cheerio.